Decrease and conquer technique in solving algorithms. I'm Efina and I'll be presenting you this topic. The topics of discussion in this presentation will be what is a decrease and conquer technique, the types of decrease and conquer technique, which are the decrease by a constant factor, and decrease by a variable factor. Some examples of decrease and conquer algorithms, which are the insertion sort, the Josephus problem, the binary search, the fake coin problem, the Russian pheasant multiplication algorithm, and the search in the binary search tree. Decrease and conquer technique is an incremental approach. In this approach, the smallest instance of the problem is solved first. Then, the relationship between the solution to the smallest instance to the entire problem is exploited to find the solution to the entire problem. There are three major variations of decrease and conquer technique. They are the decrease by the constant, decrease by a constant factor, and the variable size decrease technique. Decrease by a constant technique. In this, the size of an instance is reduced by the same constant on each iteration of the algorithm. Given here is the flow graph of decrease by a constant technique. The problem size of n is taken initially. At each iteration, this problem size is reduced by a constant 1. At the first iteration, the subproblem of size n-1 is considered. Then the solution is found to the subproblem of size n-1. The second iteration continues with the subproblem of size n-2, and the third continues with the subproblem of size n-3. And finally, all these solutions are summated to get the solution to the original problem. Mathematically, it could be represented as f of n equals f of n-1 multiplied by a if n is greater than 0, or 1 if n equals 0. The example of a decrease by a constant technique will be the insertion sort. Decrease by a constant factor technique. In this, the problem instance is reduced by the same constant factor on each iteration of the algorithm. An example of such an algorithm would be the binary search, in which at each iteration the problem size is reduced to half. Given here is a flow graph representing the decrease by a constant factor technique. Initially, the problem of size n is considered. At the first iteration, the problem size is reduced to half. Then the solution to the subproblem is arrived by reducing the problem size to half at each iteration. Mathematically, an example of decrease by a constant factor technique could be given as a power n equals a power n by 2 whole squared if n is positive and even, or a power n-1 by 2 whole squared multiplied by a if n is odd, or 1 if n equals 0. Variable size decrease technique. In this, the size reduction pattern in an algorithm varies from one iteration to another. An example of variable size decrease technique is the Euclid's algorithm. Euclid's algorithm finds the greatest common divisor of two positive integers. Let us consider the positive integers to be m and n, where m is greater than n. Then, by Euclid algorithm definition, GCD of m and n equals GCD of n m mod n, where the mod operator finds the remainder when m is divided by n. The Euclid's algorithm could be written in three simple steps. Step 1. If n equals 0, return the value of m as the answer and stop. Otherwise, proceed to step 2. Step 2. Divide m by n and assign the value of the remainder to r. Step 3. Assign the value of n to m and the value of r to n. Iterate by proceeding from step 1. An example of Euclid algorithm with numbers m equals 60 and n equals 24 is as given here. As noted in Euclid's algorithm, at each iteration, the size reduction takes place as m mod n. Let me walk through few algorithms that apply decrease and conquer technique. Insertion sort is another quadratic sorting algorithm with the time complexity of big O of n squared. At each iteration, the insertion sort selects one element in the unsorted array of n elements and places it at the correct position in the sorted array, thus creating a subarray of sorted elements. Generally, on the ith pass through the unsorted array, the algorithm creates a subarray of n minus I sorted elements. Here is an illustration of insertion sort with an example. The unsorted array contains 10 elements. The first element 8 is selected and a subarray of sorted elements is created. The second element 2 is selected and is placed in a sorted order in the sorted subarray. Then the third element 5 is selected and it is placed in its position in the sorted array. This proceeds till all the elements in the unsorted array are selected and placed in its exact position in the sorted list. Given here is the algorithm for insertion sort. An array A of n element is the input to the insertion sort algorithm. The output of the insertion sort algorithm is the array A ordered in a non-decreasing fashion. The insertion sort algorithm given here consists of a nested loop structure with the outer for loop and inner while loop. With the outer for loop, the element is selected from the array A that will be placed in the sorted list. The inner while loop finds the position of that element in the sorted list. The time complexity of the insertion sort is big O of n squared. Josephus problem. Let n people numbered 1 to n stand in a circle. Start a grim count with person number 1 and eliminate every second person until only one survivor is left. The solution to Josephus problem is a decrease by a constant factor algorithm. The algorithm that solves the Josephus problem finds the last person who's left after all the eliminations when n persons stand in a circle. The table given here derives the logic behind the Josephus problem. Suppose when one person is considered as input to the Josephus problem, no elimination happens and that person is left at last. When two persons are considered as input to the Josephus problem, the second person is eliminated and the last person left in the circle is the person numbered 1. When three persons are input to the Josephus problem, they are allowed to stand in a circle. The second person is eliminated, followed by the first person, and the third person is left behind. Similarly, when four persons are input to the Josephus problem and they are allowed to stand in the circle, the second person is eliminated, followed by the fourth person, followed by the third person, and the first person is left at last. Hence, deriving the logic, the person left would be 2L plus 1, where L is the displacement from X, which is the preceding perfect power of 2 to the input number n. There is also another simple logic behind the Josephus problem. Take the binary representation of the initial number of person, which is n. The person who is left behind could be obtained by a 1-bit cyclic shift left of n. For example, if 6 persons are input to the Josephus problem, the person left would be 5. That is, when 6 is represented in binary, it is 110. A cyclic 1-bit shift of n will be 101, which is 5. Similarly, when the input number of person is 7, the cyclic 1-bit shift left of binary will be 7 itself. Hence, the last person left in the Josephus problem will be the person who's numbered 7. Binary search is an example for decrease by a constant factor algorithm. Using binary search, an element is searched in a sorted array of n elements. At each iteration of binary search, the problem size is reduced by half. How? At the first iteration of binary search, the middle index of the entire array is found and the element stored at that middle index is compared with the search element. If the search element is less than the middle element, then the first half of the array is considered for search in the next iteration. If the search element is greater than the middle element, then the second half of the array is considered for the next iteration. This is continued until the element is found or the last element does not match the search element. Let us see the example given here. The element 70 is searched in the given array. The middle element when the entire array is considered in the first iteration is 55. 70 is greater than 55, so in the second iteration, the second half of the array is considered for search. The middle element in the second half of the array is 81. 70 is less than 81, hence the first half of the array considered in the second iteration is considered for the third iteration. Now the middle element is 70, which matches with the search element. Please note that in a binary search, the array is in the sorted order. And at each iteration, the problem size is reduced by half. An algorithm for binary search is as given here. The input to the binary search algorithm is a sorted array A of n elements and a search key k. The output of the binary search algorithm is the search key k if the key k is found in the array, or -1 if search key is not found in the array. The algorithm consists of a while loop in which the middle index is found at each iteration. The element at the middle index is compared with the search key k. If it matches, the search key k is returned. Else, the half of the array in which the search should proceed in the next iteration is selected, and the search continues. The time complexity of binary search is represented by the recurrence equation T of n equals T of n by 2 plus 1. Solving this recurrence equation using Master's theorem, the time complexity of binary search is obtained as theta of log n. Fake coin problem is an example of decrease by a constant factor algorithm. The fake coin problem statement states that among n identical looking coins, one is fake and that coin should be found. Let us assume the fake coin to be less in weight. The most natural idea for solving this problem is to divide the n coins into two piles of n by 2 coins each and do the search recursively in the pile of coins that has the less weight. So, similar to the binary search, the recurrence of the fake coin problem is T of n equals T of n by 2 plus 1. Hence, the time complexity of the fake coin problem is represented as theta of log n. Russian peasant multiplication algorithm is an example of decrease by a constant factor algorithm. The input to the Russian peasant multiplication algorithm are two positive integers m and n. The output of the algorithm is the product of m and n. The Russian peasant multiplication algorithm considers a table of two columns and each of the positive integer is written at the head of each column. The entry in the first column is halved and the entry in the second column is doubled, and a new entry is made in the table until the entry in the first column is 1. Then the number in the first column is even, cross out the entire row. For all the first column odd entries, add up the numbers in the second column and the total is the product of the original numbers. Here are two examples of Russian peasant multiplication algorithm. According to the algorithm, multiplication between two numbers is done making table entries. The table considered in Russian peasant multiplication algorithm consists of two columns. Each value to be multiplied is made as an entry in the first row of the table, and each successive row in the table is created by dividing the first column value by 2 and multiplying the second column value by 2 in the previous row until the first column value is 1. So considering the first example where the numbers are 50 and 65, these numbers are entered in the first row, each occupying one column. The second row is formed by dividing 50 by 2 and multiplying 65 by 2. So the second row entry is 25 and 130. The third row is formed by dividing 25 by 2 and 130 is multiplied by 2. So the third row entry is 12 and 260. This process is repeatedly performed until the first column value is 1. Now we will eliminate the rows that has even numbers in the column 1. So we will eliminate the row which contains 50 in the first column, which contains 12 in the first column, and which contains 6 in the first column. Now the multiplied value of 50 and 65 is obtained by adding the second column values in the table, which is 130 plus 1040 plus 2080, which equals 3250. Similarly, in the second example, we multiply numbers 49 and 61. So 49 and 61 becomes column values in the first row of the table. The second row is formed by dividing 49 by 2 and multiplying 61 by 2. So the values are 24 and 122. This is performed until the first column value is 1. Then eliminating the rows which has even numbers in the first column, we eliminate the row which has 24, the row which has 12 in the first column, the row which has 6 in the first column. Adding the second column values in the remaining rows, we get the product of 49 and 61, which is 2989. The search operation in the binary search tree is an example of decrease by a constant factor algorithm. In a binary search tree, at every node, the left subtree contains smaller values than the node value, and the right subtree contains larger values than the node value. Given here is an example of binary search tree. When the root node value is considered, its left subtree, which is highlighted, has smaller value than the root node. That is, 3, 9, 17 and 20 are smaller than 45. And when you consider the node 9, its right subtree contains values 17 and 20, which are larger than 9, and this subtree is highlighted. Here is a recursive search algorithm in binary search tree. The input to the algorithm is the root of the binary search tree and the search element k. The output of the algorithm when the search element is found is the search element k itself, and when the search element k is not found, the algorithm returns a null value. The algorithm has two base cases. That is, if the search element is not found, that is, when root equals null, it returns the null value. If the search element is found, that is, the search element k matches the data at the root, then it returns the data at the root. It contains two recursive calls. That is, if k is less than the data at the root, the algorithm recursively calls itself with the left child of root and the search element k. If the search element k is greater than the data at the root, then the algorithm recursively calls itself with the right child of root and the search element k. The worst case time efficiency of recursive search in BST is big O of n, and the average case time efficiency of recursive search in BST is theta of log n. To summarize, in this presentation, various types of decrease and conquer algorithm and few examples for each type are discussed. Thank you.